Hello AP Chemists! In this video, I'm going to be going over kinetics, practice set number 1, and that is going to go through collision theory and reaction mechanisms. So to get started, I'm going to look at collision theory, and I need you to know the 3 requirements for a successful collision. And so anytime we're talking about a successful collision, there are 3 things that you always need to consider. You need to consider that the collision must occur. Okay, and that sounds pretty obvious, but it has to happen, right? The particles have to hit each other. Second, the orientation must be correct. Okay, so there has to be correct orientation when they hit, and the collision has to have enough energy to overcome the activation energy. Okay, so then it says, using your knowledge of collision theory, explain how a reaction that is thermodynamically favorable may not occur at lower temperatures. So maybe it is thermodynamically favorable, and so we think that it should favor the formation of products. But we've talked about sometimes the activation energy is too high. And so we could say that at lower temperatures, the collisions may not have enough energy to overcome the activation energy. In other words, the activation energy is too high, at least at that temperature. So if we heated it up, then we would have more successful collisions, or at least that's what we would think. So also we've talked about how for a collision to be successful, the reactants must collide in the correct orientation. And I wanted you to draw a collision between the reactants with the correct orientation. So this is kind of a weird question, or one that we haven't really looked at yet, at least in class. But what I want you to see here is that if we're looking at these two reactants, we need to look at what bond needs to form. And what I see is that I have 3 of the bonds between the blue and white circles. Okay, so to me, that means that I need to form a bond between this white circle and this blue circle and overall break that bond. Okay, in order for that to happen, and my drawing is in no way going to be fantastic. Okay, but I would need this to collide with that end of another molecule of that. And so what's going to end up happening, like I said, is this new bond ends up forming. This bond would end up breaking, okay? And we would end up with the 2 products that are listed here. Next, it asks, why would the reaction between NO2 and F2 not occur in a single step? Use collision theory and the collision shown below to explain your answer. So this collision below shows 3 particles. So we call that a termolecular collision. Okay, and remember that this is unlikely or rare. Okay, because the chance of three molecules colliding with correct orientation and I should say enough or sufficient. And enough energy to overcome the activation energy is just highly unlikely, right? That's a very low probability or a low chance. And so that's why we would not see this happen in one step, because 2 NO2 molecules are not going to collide with an F2 molecule at the right time with the correct orientation, like it's illustrated there. Okay, so that all has to kind of happen for that to work out. Next, I'm going to talk about reaction mechanisms. And a reaction mechanism occurs in a series of elementary steps that add up to the overall balanced equation. One thing that you need to be able to do is to write rate laws for an elementary reaction. So number 5, it says to write the rate law for each of the following elementary reactions. Remember that we're concerned with the collision that is occurring. And when we write out a rate law, we write that rate is equal to K, which is the rate constant, times the concentration of whatever is colliding in the reactant side. So that would be NO times the concentration of O2. In the next example, we have rate is equal to K, which it always will be. And the thing that is colliding is just NO, right? I just have NO, so this would be the concentration of NO, and I would say that that's squared, and that is just coming from that coefficient. The last one I have would be rate is equal to K times the concentration of N2O4. In this case, a bond is breaking, okay, but there isn't actually a collision that's occurring in order for this reaction to occur. Okay. In number 6, it says to consider the following reaction mechanism, and it asks us to write the overall balanced equation for this reaction mechanism. So I'm going to first cross out things that appear on both the product side and the reactant side. Okay, in this case, that occurs with C4H9 plus, and we see that it happens again with this right here. Okay. Nothing else crosses out, and so I'm going to write it as is from there with all of my reactants or things on the left side of the arrow, and then I'm going to write everything that would be on the other side of the arrow, making this my overall balanced equation for this reaction. Part B says, what are the intermediates and or catalysts? So intermediates are things that are produced in an early step and then consumed in a later step. So here, this is produced in an early step and consumed in a later step. That would make this an intermediate. So that's C4H9 plus. Okay. Also, this is produced in an earlier step and consumed or used up in a later step, also making that a reaction intermediate. So this would be C4H9OH2 plus. Okay, for your reasoning, you're talking about both of these are produced in an earlier reaction or step in the reaction mechanism, and then consumed or used up in a later step. If I'm writing a rate law for a reaction mechanism, remember that the step that I want to look at is the slow step. That is going to be the rate determining step. Okay, remember you're only as fast as your slowest rate. You're only as fast as your slowest lap in a relay race. Okay, so rate is equal to K times the concentration of C4H9Br. I just wrote the rate law for the first step, for the first elementary step. In number 7, it says the reaction 2NO plus O2 yielding 2NO2 exhibits the following rate law. In part A, it says, why would this reaction not occur in only one step? Okay, we've talked about this before, and I'm not going to write a long response here, but this is termolecular, okay, and it's 3, but it's also that there are 3 or more, I guess I should say 3. There are 3 particles that would have to collide here. That is highly unlikely. In part B, it says, which of the following mechanisms is consistent with this rate law? Okay, so the rate law that it's talking about is this rate law up here. And so I'm going to find the rate law for each of these mechanisms. So for the first mechanism, I'm looking at my slow step, as I always will. And that rate law would be rate is equal to K times the concentration of NO times the concentration of O2. That does not match the mechanism above. Okay, the second step, the slow step is second. Okay, that makes this one a little bit more complicated. Okay, if I'm writing out my rate law for this, it would be rate is equal to K times the concentration of NO3 times the concentration of NO. Now remember that a reaction intermediate cannot be in the reaction, or in the rate law, sorry. And so I'm going to basically just set these two equal to each other. Okay, I'm going to change my color. I'm going to set these two equal to each other and solve for the intermediate. So NO3 is equal to NO times O2. And yes, there are Ks and things like that to also consider, but just to make it simple, we can just do it that way and then just plug those in to my rate law. That would make this rate is equal to K times the concentration of NO times the concentration of O2 times the concentration of NO. And lo and behold, there's two NOs, so that would be NO squared times the concentration of O2, which actually does match the rate law that we were given. So mechanism 2 does match the rate law. Okay, and mechanism 3, oh, thank goodness. We have a slow step again for the first step. These are always much, much easier. So this is rate is equal to K times the concentration of NO squared. Okay, once again, that does not match the rate law. And then lastly, oh no, it's a second step. Okay, I can write out my rate law. My rate is equal to K times the concentration of N2O2. Okay, N2O2 is a reaction intermediate, so we cannot do that. So I'm going to set that fast equilibrium state equal to each other. So basically I'm saying that NO squared is equal to N2O2. And so I can therefore plug that in here, and that would be rate is equal to K times the concentration of NO squared. Once again, that does not match the rate law. So the only mechanism that was proposed that is consistent is mechanism 2. You could have more than one mechanism that is consistent. At that point, you would want to use experimental data to evaluate the mechanism, and that is something that we will talk about in a future lesson. Okay, oh man, I split this on the page. That's okay. So the next part, it says that the overall reaction for the decomposition of ozone is as follows. For number 8, it says the reaction mechanism for the decomposition of ozone without a catalyst is as follows. It says identify the intermediate in this mechanism. Okay, so hopefully this is starting to feel repetitive, but hopefully you're also starting to see what the intermediates and things like that would be. So we see that O is produced in an early step, and then it is consumed in a later step, making that a reaction intermediate. For part B, it says the rate law for the decomposition of ozone is determined to be rate is equal to K times, and you see the rest of that. It says which step is the slow step, and justify your answer. If the first step is the slow step, then the rate law would be the constant rate is equal to K times the concentration of O3. Okay, obviously that's not the answer, so the second step must be the slow step. Okay, now to show my work for that, if I had my rate law for that second step, I end up with this. Now, obviously, the problem there is that it has a reaction intermediate in it. And so I'm going to set my fast equilibrium step, because I would have to assume that that is fast and at equilibrium if my second step is slow. Okay, and you see those equilibrium arrows there as well anyway. And the forward reaction is equal to the reverse reaction in terms of the rate And like I said, obviously we would have the K's there, but I'm just kind of ignoring them. I'm going to solve for the concentration of my reaction intermediate, and I end up with O3 concentration over O2. So then when I plug this in, that's rate is equal to K times the concentration of O3 times the concentration of O3 over the concentration of O2. Okay, if I rewrite this, this would be rate is equal to K times the concentration of O3 squared times the concentration of O2 to the negative 1 power, since O2 is in the denominator. Okay, so that is what I would have there. So that is consistent with the second step. So that's the rate law for the second step being slow, and that is the rate law of the reaction. So it ends up working out. Okay, for number 6, which is number 9. Oh boy. Okay, so that is number 9. So it says, what is the overall reaction when I have chlorine in this? So I'm looking for things that can cancel. Cl is going to cancel on both sides. ClO is going to cancel on both sides as well. That leaves me with O3 plus O yields 2O2 gas. Okay, then it asks me to then it asks me to identify the intermediate in this mechanism. So the intermediate is ClO for all of the reasons that we've already talked about, so you can figure that one out. For the catalyst is actually Cl, and the reasoning for that is it's consumed in an early step, and then it's produced in a later step. Okay, meaning that it was not consumed by the reaction, and so it is used in the mechanism but not consumed in the reaction. Then it says to write the rate law for this reaction. So the first step is the rate determining or slow step. So since it's the first step, that would be rate is equal to K times the concentration of O3 times the concentration of Cl. So we've talked about reaction intermediates and how they cannot be in a rate law. A catalyst can be in a rate law. So the concentration, the more catalyst you have, the faster the reaction can happen, which makes sense, right? In biology, you kind of talked about how enzymes are kind of limited by the concentration of it. And if you have more enzyme, then more substrate could be used up or could react. In number 9, which I think is number 10, whatever, my numbering abilities is ridiculous. It says, here's the reaction profile for the decomposition of ozone without chlorine. It says, is the reaction endothermic or exothermic? I'm not going to explain my answer here, but I'm not going to write it. But you see that the energy of the products is lower than the energy of the reactants, so energy is released, so it is exothermic. It says, on the graph above, draw the reaction profile for the decomposition of ozone in the presence of chlorine. Okay, so if I were drawing this out, one thing that I see in my reaction mechanism, okay, we said that this first step is the slow step, and it happens in 2 different steps. Okay, so things that I want you to notice is that that first step has a higher higher activation energy than that second step does. So that is indicating that it is my slow step. Notice that also with the catalyst that my activation energy decreased from that red bump that I have, the red reaction profile, because adding a catalyst should lower the activation energy of the reaction. And then also notice that the energy at the beginning of the reactants and the products is still the same, right? We still have the same reactants, we still have the same products. Really, it's just a different pathway that got us from the reactants to the products. And then lastly, it says, using your knowledge of collision theory, explain why the decomposition of ozone occurs at a greater rate in the presence of Cl. And so there we're just kind of talking about, catalysts once again. And so I'm not going to go through too much with that. All right. Bye, guys. Bye, y'all.